This is chapter 7.5, which is multiple angle and product to sum formulas. There's actually quite a bit of formulas introduced in this section. And what I really want to do is I want to try something a little different here. I'm going to just kind of hit you with all the formulas at the very beginning, and then we'll see a few examples of each one after the fact, and we'll have to recall which formula is applicable. So in doing this, you kind of have to go back and forth to see what the formulas were, or if you have a sheet in front of you, that's fine, or you can write them down and pause, of course, and do that. But here are the double angle formulas, and just like everything I show you, I would always love to prove if there's time, but let me just say that these formulas are actually pretty easy to derive based on the summation formulas for sine, cosine, and tangent, only where alpha and beta, as I call them, are each equal to theta. You get this for sine, that for cosine, and this for tangent. Now, cosine is funny because there are three versions, but notice if you just take the advantage of the fact that 1 minus sine squared is the same as cosine squared, you get from the first to the second. And similarly, if you remember that sine squared is the same as 1 minus cosine squared, of course I'm using the Pythagorean identities, then you can get from the first to the third. So that verifies those. And the power reducing formulas then are actually legitimately just from this. In fact, really they're from this one for cosine of 2 theta. So notice if you solve for sine squared using the second version of cosine of 2 theta, you'll actually get this. Similarly, if you solve for cosine squared using the third variation, you'll get the second one for power reducing. And by the way, what power reducing does for us is it gets rid of a power of sine, cosine, or tangent. And then finally, the tangent squared power reducing formula is pretty easy to verify because tangent squared is sine squared over cosine squared. So literally, if you just do this over that 1/2's canceling, you legitimately get 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. So that's not too bad. Half angle formulas are a little funny. And again, they're pretty easy to verify because literally all we're doing is square rooting each of these. When you square root, you get a plus or minus. Tangent's a little different, but it is actually doing the same thing, but there's a little bit more of Pythagorean identities that can come to play to getting rid of the plus or minus actually. But with sine and cosine, you need the plus or minus. And to get rid of the radical as well with tangent. But again, with sine and cosine, you need the plus or minus. And what the plus or minus corresponds to is where the angle lands as far as quadrants go after you half it. So for instance, let's say theta is 200 degrees. That would be somewhere over here in the third quadrant. But if you want to take sine of half of 200 degrees, well, half of 200 is 100 degrees, which would actually be somewhere in the, well, it would be in the second quadrant. And since sine is positive in the second quadrant, then sine of 200 over 2 would be positive. So that's what you have to do. You have to basically check where the angle lands, and if sine or cosine, depending, is positive or negative in that quadrant. Okay, so like I said, I wanted to show you all the formulas. These are just 3 sets. There's 2 more I want to show. There's product to sum and sum to product, so let's take a look at those right now. Okay, so here are finally the product to sum formulas and the sum to product formulas, so I guess I'll just box these. But as far as explaining where they come from, it's not too difficult to tell. Basically, they come from the sum and difference formulas of sine and cosine. So for instance, if you take the sum of angles of cosine of the sum of angles, and cosine of the difference of 2 angles, and you take the difference of those 2 results in this order, and half that, you get the product of sines only, because the product of cosines will cancel out, if you recall what the sum and difference formulas for cosine look like. And there's very similar arguments for the rest. So really that's where it comes from. Now, product to sum, well, product to sum actually has to do somewhat with half angle as well as sum and difference. And you can kind of see. So these aren't actually too hard to verify, because with this we have the half angle formula to get rid of the over 2 part, and then we can use a sum or difference formula for each of these, and then verify that they are indeed the same. There's obviously some heavy cancellation that happens in verifying that, but anyways, these aren't too bad to verify. So now, finally that I've introduced to you all of the formulas that we need to see for 7.5, we'll do some examples. I'll try to make sure we hit each one, but I'll be quite honest with you. At this level, product and sum to product aren't really used too much. That's more for a particular type of problem that comes up in calculus, but at least we know that they exist, and we've at least seen them. As far as seeing examples, I'll see if I can do one or two examples of them, but I don't want to make the video too long, so just kind of warning. So now let's take a look at some examples. So the first type of problem I want to cover is one that involves solving for a variable, so let's see if we can do this. Here we're asked to solve for x. Notice there's double angle formulas, well, double angle trig functions in place here. So I'm going to have to use the double angle formulas to make them in the same argument. Because remember, our goal is to solve for whatever trig function. So in this case, it seems like we want to solve for sine first, and then solve in one rotation, and then add 2 pi k to each solution. But to do that, we need to get sine of x, not sine of 2x. So this tells me to use the double angle formula for sine, which is 2 sine cosine. And now this we can definitely solve. Just pull out sine, so factor out sine. So we get sine of x times 2 cosine of x minus 1 equals 0. So this implies either the first product is 0, so sine is 0, or this is 0. Notice when 2 cosine of x minus 1 is 0, add 1 and divide by 2. You'll get cosine of x is equal to 1/2. So now solving in one rotation of the unit circle for each one. Sine is 0 at pi and 2 pi. Well, I guess 0 and pi, I should say. And cosine is positive 1/2 at pi over 3 in the first quadrant. Remember that cosine is also positive in the fourth quadrant, which would be 5 pi over 3. Perfect. Now all we need to do is add 2 pi k to these. But notice 0 and pi, if you add 2 pi k, you get 2 pi k and pi k plus 2 pi k. So really what that means is the odd multiples of pi and the even multiples of pi, well, vice versa. So this would be the even one instead of the odd. But in any event, what we end up getting is just pi times k. So all multiples of pi, positive or negative, even 0, are the zeros of sine. And then here we'll get pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k, where k is an integer, meaning positive or negative whole number, and this is right here is the general solution. So this solution is within one rotation of the unit circle, if you will, and here this is a general solution. Good. So now 1 wasn't too bad. 2 seems a little funny, because we could try to use the, let me see how we could tackle this. We could try to use the double angle formulas right away, but then we have to square it out, and when you use double angle formulas, it gets really long on the inside, and I don't want to square out some crazy long expression. At the same time, we could square root both sides, but notice when you square root 1, you get a plus or minus 1, and then you'd have to you'd have to solve two different equations at the same time. So in my opinion, the best way of doing this is by expanding out first. So what we end up getting is sine squared of 2x plus 2 sine 2x plus, sine 2x, cosine 2x, there we go, plus cosine squared of 2x, and then equals 1. Now what we want to do is we want to get everything in terms of one variable only, in other words, in terms of either sine or cosine. This seems a little tricky. I mean, something that I do notice that we can definitely do is, oh, look at this. What's sine squared plus cosine squared? Sine squared plus cosine squared is 1, so this becomes 2 sine x cosine 2x, 2 sine 2x cosine 2x, plus 1 equals 1. So if you subtract by 1 to both sides, you just get 2 sine of 2x times cosine of 2x is equal to 0. And now you can just see when sine is 0 and when cosine is 0. And in fact, something I want to show you that I think is a little better, in my opinion, is to just look at, what this expression looks like as far as a double angle formula goes. Now, remember the double angle formula I used here, I didn't write it down, but again, you can go back and verify what it was. It was this. Sine of 2x is 2 sine x cosine x. And look at this. 2 sine times cosine of the same argument, 2 sine times cosine of the same argument is sine of double that angle. So that means we can actually write this whole thing, believe it or not, as sine of double the angle. Now the angle here is 2x, so if you double that, you get 4x. And we already saw that the multiples of pi are when you have zeros of sine. So the inside of sine, 4x, is any multiple of pi in order for sine of that to be 0. So again, the only zeros of sine are multiples of pi. So that means the argument has to be a multiple of pi. So we have 4x is equal to pi k. Then, dividing by 4, and I guess you could write plus 2 pi k. Trying to see how that would work. No, I guess this is okay. This is okay. And then divide by 4. And you end up getting that x is equal to just the multiples of pi over 4. Now, if this sounds funny, it's actually not that hard to verify this is indeed the case. Because look, when sine is 0 is at multiples of pi, so 0 or pi. So if you think of one rotation, 0 and pi. Okay. When is cosine 0? Cosine is 0 at multiples of pi over 2. So cosine of pi over 2 is 0, and cosine of 3 pi over 2 is 0 as well. So that means 2x is either 0, pi, or pi over 2, or 3 pi over 2 in one rotation. But if you divide by 2, then you get exactly the multiples of pi over 4. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which is back to pi, and then it goes on like that. So again, something you can verify on your own doing it the other way, but using the double angle formula, a lot of the work was kind of squashed into just one nice expression. Instead of us having to write out 4 different things and writing plus 2 pi k to each of them. So it's really nice recognition that we can do that. So now let's take a look at a different type of example. All right, so here we're asked to find the exact values of sine, cosine, and tangent. Let's take a look at the first one. So we want to find the exact value of sine, cosine, and tangent of pi over 8. Now, pi over 8 is half of pi over 4. So this is pi over 4 over 2, basically. It's half of pi over 4. So that being said, we need to use the half angle formulas for sine and cosine. And then once we have sine and cosine, we can just divide to get tangent, of course, because tangent, of course, is sine over cosine. So let's see. So sine of pi over 4 over 2, according to the half angle formula, is plus or minus the square root of 1 minus cosine of pi over 4. I meant to say, well, I said over 2, but I wrote 4 for some reason. Okay, over 2. Now, is it plus or minus? Well, pi over 8 is actually in the first quadrant, so with that being said, we're actually going to use the positive root. Perfect. And similar for cosine. So cosine is actually also going to be positive. So yeah, let's see if we can do this. So cosine of pi over 4 is radical 2 over 2. So we're going to get 1 minus radical 2 over 2 over 2. If you multiply top and bottom by 2 to clear denominators and distribute this into the top, what you end up getting is, let me just erase for space here. In the numerator, you end up getting 2 minus radical 2. In the denominator, we get radical 4, which is 2. So this is the value for sine. Perfect. So that's sine of pi over 8. Let me just label that as sine. I don't really have too much space here, but I think we're okay actually. Because cosine of pi over 4 over 2 is, again, it's going to be positive because we're in the first quadrant. Pi over 8 is in the first quadrant. Sine and cosine are both positive there. And then this is going to be radical 1 plus cosine of pi over 4 all over 2. So notice sine has a negative in the inside, but cosine has a positive on the inside. And let's see, cosine of pi over 4 is radical 2 over 2 again. So we really just get the same thing, only with a minus, plus instead of a minus on the inside. So we multiply top and bottom by 2 in this radical. After distributing this, we end up getting radical 2 plus radical 2 over 4 now. Radical 4, which is 2. Good. So it is the same thing, only with a plus instead of a minus on the inside. And now what is tangent? So this is cosine. Now, since tangent is sine over cosine, all we need to do is multiply this by the reciprocal of that. So for tangent, what we really end up getting is the following. This times the reciprocal of this, the 2's cancel, so we end up getting the square root of 2 minus radical 2 over 2 plus radical 2. Now, this is not rationalized. Technically, it's a radical over radical, but I wrote it as one radical. If you multiply top and bottom by the denominator, by the radical in the denominator, you can rationalize it. And it's kind of nice because you'll get a difference in squares, but it'll allow you to verify that on your own, of course, because I'm out of space. But I'm going to move on. This is acceptable, I guess, just depending what the wording is. If you need to rationalize, then you can do that. But I'm going to move on. So here it says, find the exact values of sine of 2 theta, cosine of 2 theta, and tangent of 2 theta, given the sine of theta is negative 3 over 5, and specifically it says that theta is in between 3 pi over 2 and 2 pi, meaning that it is in the fourth quadrant. So right here is where we lie. Which makes sense because sine is negative there, and it's no coincidence that it's given the sine is negative 3 over 5. Good. But now what? Well, I guess something that we can do is we can actually find cosine and tangent in that quadrant as well. So that's something we kind of have to do here. So let me do that off to the side, I guess. Let me erase this real quick. All right, so if we have our angle theta, I mean, this is really going to be the reference angle, but let's just say it's theta just so we know what we're talking about. Sine of theta is negative 3 over 5, and it's opposite of our hypotenuse, so it's negative 3 over 5 like this. Good. Cosine would have to be positive because it's in the fourth quadrant. And if you use Pythagorean theorem, notice 3 squared plus 4 squared will equal 5 squared, so this has to be 4. Good. And now we can find all of the other ones. So we know, I guess that's fine. So we know sine is negative 3 over 5, that was given. Now we know cosine is 4 over 5 because it's adjacent over hypotenuse. And tangent is then what? Tangent would be, well, opposite over adjacent, which is negative 3 over 4. Real kind of small, but hope we can make that out. That's a 3. Okay, good. So in this case, then for sine of 2 theta, we'd have to use the double angle formula for sine of 2 theta, which is 2 times sine theta cosine theta. And we know what sine theta cosine theta are from what we summarized over here. So this is going to be 2 times negative 3 over 5 times 4 over 5, which amounts to negative 24 over 5. Negative 24 over 25. Perfect. So this right here is sine of 2 theta. Now, just to keep in mind what this means as far as the sine goes, if you double something in the fourth quadrant, where will it land you as far as quadrants go? If you double each side of this, well, this inequality that is, double 3 pi over 2 is 3 pi, double 2 pi is 4 pi, so it's going to be in between 3 pi and 4 pi, which is actually in the third or fourth quadrant. So if theta is in the fourth quadrant, then when you double it, you get back either in the third or in the fourth quadrant. But sine is negative there, so this actually works. So it just kind of goes to show that with half angle formulas, you have to check for the sign because of the plus or minus, but with double angle formula, it just magically so happens to work, which is kind of interesting. And now for cosine of 2 theta, well, we can actually use whichever one we want. But remember, there are 3 variations. I'm just going to use the one that involves sine. So it was 1 minus 2 sine squared. So it's 1 minus 2 times, well, let's see, sine is negative 3 over 5, so it's negative 3 over 5 squared. So it's going to be 1 minus 2 times, I guess that's 9 over 25, which is 1 minus 18 over 25. And since 1 is 25 over 25 as a fraction with denominator 25, we end up getting 7 over 25 in total. And notice that's positive, and you can kind of see why. And again, cosine is only positive in the fourth quadrant. So that actually tells me that this angle in particular will actually be only in the fourth quadrant. And we'll actually see from tangent's double angle, because remember, tangent is only positive in the third quadrant. So if this suggests that 2 theta would end up in the fourth quadrant, then tangent better be negative. Well, tangent of 2 theta better be negative. So let's take a look at that. And in fact, that's actually really simple to do. We don't even need a double angle formula for tangent. We can just do sine over cosine. And notice negative over positive is indeed negative. So that's this times the reciprocal of that. The 25's cancel, and we get negative 24 over 7 for tangent of 2 theta. All right. So I've done 4 examples already, and the video is getting kind of long. But there's one type of problem that I really want to show that will involve the product to sum formulas. So actually it's sum to product. But let's take a look at that right now. All right, so the one I actually wanted to take a look at specifically was this problem here, because this will of course involve a sum to product formula. But I figured it'd be worth it to go over one that involved the product to sum. So I have these 2 types of problems, but notice that this is in particular when it comes to solving. If you have a product already equal to 0, that should actually be pretty easy to solve using the zero product property. So that's the idea here. We want to get this to be a product. So to use the product to sum, or sum to product formula, so let's see if we remember. It's going to be 2 times cosine of the angles added together divided by 2 times sine of the difference between them. And of course, verifying this by having a sheet in front of you will definitely help. I certainly don't remember these things, so I kind of have to do that. In fact, it should be the other way around. This should be sine and this should be cosine. Okay. Good. So now let's see if we can go from here, and of course it's equal to 0. Since it's times 2, we can divide both sides by 2, that's fine. And this is going to be, let's see, this is going to be sine of, well, the top is 8x, 6x plus 2x is 8x, over 2 is just 4x. And this will be cosine of, the difference here is going to be 4x divided by 2 is 2x. All right, so either sine is 0 or cosine is 0. And again, there was a 2 in front, but if you divide by 2, it doesn't really make a difference in the equation. So either we get 4x is equal to 0, well, maybe not 0, but sine of 4x is equal to 0. So let me write that. Sine of 4x is equal to 0. Or cosine of 2x is equal to 0. Trying to see if there's another way we can do this. Something kind of interesting happens, but I don't think it's too crazy to talk about. Well, let me just say this. Cosine of 2x being 0 actually implies that sine of 4x would be 0. Because sine of 4x, using the double angle formula, is 2 sine 2x times cosine of 2x. So if we actually replace this with that, we get 2 hits of cosine of 2x. But more importantly, that's already contained in this. So we'll actually see that when solving. So notice, when is sine 0? Sine is 0 for any multiple of pi. So that means 4x, its argument must be pi times k. Here, when is cosine is 0? When is cosine 0? Cosine is 0 when it's inside is a multiple of pi over 2. So either it's pi over 2 or 3 pi over 2 in one rotation. So let me write it like this. It's pi over 2 plus 2 pi k, or 3 pi over 2 plus 2 pi k. But really you could just write it like this, pi over 2 plus pi k. Because if you think about it in the unit circle, if this is pi over 2 and this is 3 pi over 2, here and here, that's where cosine is 0. But notice, since they differ from pi apart, if you add pi from this one, you get this one. If you add pi again, you get from that one to that one. So hitting all of them is just adding a multiple of pi, so plus pi k. But now when you divide through by 4, or by 2, and by 4 here, what do you get? Here you get x is equal to pi k over 4. Here you get x is equal to, well, pi over 4 plus pi k over 2. And if you actually wrote these out, well, they're not entirely the numbers you'll get here, but they're included in this list. So this is pi over 4 plus any multiple of pi over 2. So since pi over 4 lies here, let me do that a little better. There we go. Since pi over 4 lands you here, so these are the multiples of pi over 4. This is pi over 4, 5 pi over 4. Actually, it's 3 pi over 4. 5 pi over 4, and 7 pi over 4 finally. Well, notice these are pi over 2 apart. So adding pi over 2 to each of these angles gives you the next one. So in reality, this is actually the same as this list, which is kind of funny to think about. Yeah, so they both actually have the same solutions. So you don't necessarily need to write both of these. If you wrote the list out, you'll actually get the same list. They're just different ways of writing it. So I'm actually going to box this one because I think this is a little nicer looking. So anyways, with that said, I'm going to erase this and move on to the next example now. And so here we're actually asked to write this as a sum or difference. Now in the case of sine times sine from the product to sum formulas, this is actually going to be a difference. It's 1/2 times cosine of the difference of the two angles, so 5 theta minus 3 theta, minus cosine of the sum of them, so 5 theta plus 3 theta. So in total what this amounts to is 1/2 cosine of 2 theta, like that, minus cosine of a theta. So let me just write it without parentheses, I guess. Perfect. And if you distribute the 1/2, then that's really it. So we wrote it as a difference, basically. So it's not a product anymore, now it's a difference of trig functions. And I'll box this. Yeah, that's fine. Good. So that concludes 7.5. I really hope you enjoyed all the examples we saw. But again, I did a little differently. I showed all of the formulas first, and then we just went through the examples one after the other. That actually concludes Chapter 7 as a whole, and I'll see you in the next videos for Chapter 8. Thanks for watching. See you then.